What's up, ladies and boys? Today, we are going to talk about component vectors. So, until now, I've done my very best to avoid having to look at things that are pointing in two directions at the same time. And this is kind of hard to do, right? It's hard to avoid it for too long because so many things in real life just tend to be at some goofy angle, right? Most things don't go perfectly straight up and down or perfectly horizontal. Most things do a little bit of both at the same time. So, what we're going to talk about today is how to look at something that does both at the same time, and that includes all vectors. So, vectors are just a length and a direction, right? If it's in both directions at once, we can find both those directions. So we're going to talk about how do I split a single vector into its components, and that's really all we're going to trip about today. So I'm going to kind of talk generally about how to break things into components, go over some of the math that we're going to need to be able to do that. And then we're going to look at maybe like one or two easy, pretty commonplace example problems. All right. So before we can start doing this, we need to learn a little bit of math, or maybe just remember a little bit of math. For some of you, this won't be too bad. For some of you, you might go, I've never seen that, or it's been years since I've seen that. So let's talk about the math first. When we are breaking things into components, our goal is to turn things into right triangles. So, lucky for us, or luckily, maybe if I were better at English, luckily for us, right triangles follow some general ratios that people have spent a ton of time studying, and we're going to use to solve for individual pieces of our triangle. So let's go ahead and review a phrase or maybe something or other that you're going to need to know for the rest of your life. Those things are sine, cosine, and tangent. So there is an acronym. Is that the right word? An acronym that helps us remember how to set up sines, cosines, and tangents. It's SOHCAHTOA. So in math, each of these letters either represents a trig operation or the name of a side. So let's name some sides real quick. The side that is the diagonal side, the longest side that's straight across from the 90-degree angle. This has a special name. It's called a hypotenuse. Hypotenuse. I hope I spelled that right. Probably not, but you know what I mean. Then there are two other sides. These are called the legs of the triangle, but we need to distinguish one leg from the other. So we often call these either the opposite side or the adjacent side. And what we're talking about opposite and adjacent to, like what is that relative to, is whatever angle we are interested in. So in this case, I've denoted the angle we are interested in with the Greek letter theta. This is the variable we use for angles in math. We're going to see it again in physics. It means something else a little different in physics, but it's all right. We can adapt. So if we look at the leg of the triangle that is farthest from the angle we're interested in, we refer to this as the opposite side because it's on the opposite side of the triangle from our angle. And then this side here that helps make the angle with the hypotenuse, this is our adjacent side. Okay. So now to set up sines, cosines, and tangents, there's a ratio for each of them, which means a fraction, that is comprised of these sides. For sine and cosine, the denominator of both of these is always your hypotenuse. We'll put just hype for hypotenuse. For sine, the numerator is whatever the length of the opposite side is. For cosine, it's the adjacent side length. For tangent, it's opposite over adjacent. All right. So now this SOHCAHTOA business, this helps us remember these three equations. So or SOH, this is sine opposite hypotenuse. And it tells us the trig function, the numerator, the denominator in that order for all of these. So this would be cosine, adjacent, and then hypotenuse. And then T, the TOA part, is tangent, opposite, and adjacent. All right. There's a bunch of different acronyms that help people remember this. Sometimes people go, all right, SOHCAHTOA is the acronym, right? That weird word phrase is what I remember. When I was just a wee lad, a young whippersnapper, first getting his teeth into trigonometry, I had a wonderful math teacher who taught me SOHCAHTOA. I had also wonderful classmates who decided it was a good idea to share this other weird phrase to help us remember SOHCAHTOA. And if nothing else, I hope you get a giggle out of it, right? If you don't use it, if you're just like, SOHCAHTOA is good enough. My brain is vast and infinite, and I have so much storage space. SOHCAHTOA is enough for me. If not, hopefully this phrase can help you. The way I remember SOHCAHTOA is not just SOHCAHTOA, right? Well, everyone remembers SOHCAHTOA, but there's a sentence that goes with it. The sentence I learned is, some old hippie caught another hippie. Can you guess? Tripping on acid. Whoops, on. And that's how I remember SOHCAHTOA. I don't remember if my math teacher taught me that or if my friend taught me that, but either way, I still remember it. So I think it's funny. I think it's a good way to remember it. If nothing else, it illustrates the political climate in the 1970s or something. I don't know. Anyway, so we're going to use these three trig functions to find parts of vectors. So let's do that. So let's just take a nice easy example. We have a force of 20 newtons and it's being applied to a mass at an angle of 30 degrees above the horizontal. Okay, so let's draw a little picture. So mass, horizontal, our force is being applied 30 degrees above that. So that looks like maybe about 30 to me. So here's our force. This is 20 newtons. We want to know, how hard is the force pushing in the horizontal direction and how hard is it pushing in the vertical direction? Because it's doing both, right? Think about this at, like, there's a bunch of situations we could examine, right? We could have, oh no, a cat, because I can draw a cat. Dogs are a little harder. And this thing is cat-shaped, okay? And you got a leash on your cat. When you pull on this leash, you're pulling a little bit up on it and a little bit sideways on it. So it's important for us to know both strengths, right? Because if you pull too much up, you're going to kill your cat and hang it. If you pull too sideways, you'll drag your cat. I don't really know how you walk cats, but regardless, it's important to know both of them, right? So if we want to know the components of this, what we want to do is turn this vector into a right triangle. The way we do that is we go to the arrow tip, the end of the vector, and we drop a line straight down. So now this length here, this is going to be the x component, or fx, of this force. And then this length here will be the y component. So for us to find these, all we need to do is a little bit of trigonometry. Here's our 30-degree angle. So let's go ahead and find the x piece first. So we know the angle, we know theta, we know the hypotenuse, right? H equals 20. What we're looking for are, compared to the angle, the opposite side and the adjacent side of this newly made forced triangle. So if we're looking for the x, this is the adjacent side. So we need to ask ourselves, which trig operation uses adjacent, which is what we're looking for, and the piece of information we know, the hypotenuse. All right, so we go back to SOHCAHTOA. Some old hippie caught another hippie adjacent hypotenuse. We're using the cosine function. So let's set up our cosine function. Cosine of theta equals adjacent over hypotenuse. Now we're going to plug in our values. 30 goes into theta, so we have cosine. The 30 degrees goes on the inside of the cosine operation. Our adjacent is f of x. That's what we're looking for. Our hypotenuse, we know that number, it's 20. All right. So now we can type cosine of 30 into our calculator. It might be a good idea for you to double check that your calculator is right now in degrees and not radians. If you're in calculus, your calculator is probably in radians because that's what you use most often in that class. So you're going to have to be switching back and forth. I apologize. I understand how difficult that makes your life. So this cosine of 30 is approximately, and here, let me tell you, it's radical 3 over 2 if you know your unit circle. But we're going to use the decimal just because physics, you know. Cosine of 30 is about 0.866 equals f of x over 20. Multiply both sides by 20. And we get 17.32 about equals f of x. So if we are pulling at 20 newtons at an angle of 30 degrees, we are applying a force in the x direction that is 17.32 newtons. So we're applying a bunch of that force in the x direction, which makes sense, right? If we're at 30 degrees, this is much more in the x than in the y. This x piece is way longer than the y piece. And if this were like a rope, our rope would be closer to being horizontal than it is vertical. So just so we can compare, let's also go ahead and find the y component. So this is the opposite. Now you're going to say, I know the adjacent now. Can I use the adjacent? I'm going to say no, because that number has been rounded. So if you use it for another calculation, you're taking a rounded number, getting a new number, and then rounding that. So you've like double rounded. The more times you round and the more times you reuse rounded numbers, you're going to get worse and worse answers every time. So we know the hypotenuse exactly to be 20. There's no rounding or error there. So we should always use the unrounded exact answers if we can. So we're going to use opposite and hypotenuse. That trig function is sine. Sine of theta equals opposite over hypotenuse. So let's plug in our known values. Sine of 30 degrees equals, we don't know the opposite side. That's what we're looking for. F of, y divided by 20. Sine of 30, if you type that into calculator, you will find that it equals 0.5. It's 1/2 exactly. Equals f of y over 20 times 20 on both sides. So we get 10 newtons for f of y. So one thing that if you're new to trigonometry, if this is one of the first times you've ever calculated these numbers before, you're going to maybe be a little uncomfortable with some idea, right? This length here plus this length here do not add up to 20. And we can kind of see that graphically if we look at our triangle, right? If I take this piece Allow me to erase a little bit of this work here. We're not going to look at it again anyway. So if we take this piece here, there's that. And then we take our Y piece from right there. Let's take that and lay it end to end. We're going to lay it flat. So let's turn it over. And then let's lay it flat so it's end to end there. Now we're going to compare that to this hypotenuse length. Let's move this. Let's turn it so it's flat. And we'll just lay it next to it. Do you see how our hypotenuse is not as long as the full X and Y together, right? This chunk here, this is the difference between them. We can see our X, which was almost as much as our hypotenuse, is almost as long as our hypotenuse, right? Because it's at an angle, it doesn't take as much distance to travel from this point to this point because we're going in a straight line, right? There's a phrase or maybe a saying or something. The shortest distance between 2 points is a straight line. If we take this not straight line distance to get here, of course it's going to be longer than this straight line distance, right? So that's why they don't add up. It's because you're comparing two different lengths, sort of. You're comparing the long way around to the direct path. So these will never add to be this unless your angle is 0 degrees, in which case you have two things that are laying like flat on top of each other. Okay, so there's how we do some trigonometry. Let's talk about finding the magnitude of a vector. So there are going to be times where we know the components, or we can guess the components, or we'll have some sort of inkling as to what the components are. We can use Newton's laws to justify why they should be equal to something. So we'll know the components, f of x and f of y, and we'll need to find the magnitude of the force itself. Not its components, but the force. So the way we're going to do that is with good old Pythagorean theorem. So if we have a force pushing with 30 newtons horizontally and 20 newtons vertically, what's the magnitude of the force? What's the hypotenuse? So Pythagorean theorem, in case we forgot, is a squared plus b squared equals c squared. A and b are the legs. It doesn't matter if you say this is A and this is B, or if you choose to swap them. It makes absolutely no difference at all. It's all a matter of perspective. The only thing that must be in a specific place is C has to be our hypotenuse. Has to be. Otherwise, the formula doesn't work. So if we take our A and B, we're going to square them, add their squares together, and that'll give us c squared. Then we'll have to take a square root to get the hypotenuse. So we're going to have 20 squared plus 30 squared. Oh, not 30 degrees. 30 squared equals c squared. Okay. So 20 squared is 400. 30 squared is 900 equals c squared. So this is 1300. Now we take a square root on both sides to cancel the squared. I understand that most of the time when you take a square root in math, you're used to putting a plus or minus here. But this is a length of a triangle. Triangles can't be negative something long, right? If I ask you how tall you are, you don't do a handstand and then tell me you're negative 5'6", right? You just say, I'm 5'6", regardless of what position. If you're laying on a bed, you're not a different height, right? So we just throw away the negative because of some reasons, right? Because it's uncomfortable to say that things are negative something long. Most of the time, lengths are not considered to be vectors. They're scalars. So we take the square root of our... Sorry, I'm looking for the square root button on my calculator. Of 1300. And we get some goofy radical. All right, we get 36.056 equals C. So this force here is 36.056 newtons, right? You will usually get ugly decimals for at least one of the three components, whether it's one of the legs or the hypotenuse. It could be all of them. It could be none of them. There are a couple special triangles, but in general, if you get a weird decimal, that's par for the course. All right. So we know how to take a vector at a known direction and break it into components. We know how to take components and get the total vector. We're going to worry about solving for the angle later. That's a little more than I want to cover in this lecture. So now let's talk about adding components, right? Then we'll look at some application problems. So we have, when adding vectors, x components can only add to x components. And let's maybe think about that, right? Let's say I have some component that's this long. Let's say this is 3 inches, right? And then I add something perpendicular to it and make a right triangle. Let's say maybe this is 2 inches. Okay. If I look at that, if I add these together, and now my new vector is both of them combined. So start at the tail, go to the tip of the other one. It's this pink vector. And we ask ourselves, what is the x piece of this vector? That's just this. Adding this perpendicular piece doesn't change this this x length. This is still 3 inches. And no matter how I take, let me maybe change this to one of these. No matter how I take this, if I take the end and I move it up and down like this, the x is always going to stay the same no matter how far up and down I go. And that's just the way it is. I don't know why. That's just the way math works. So when we're adding, especially components, you're going to take x components, and the only other thing in that direction is other x components. So x components go with x components. Y components can only add with other y components. You're going to say, then how do I make stuff longer and shorter? Well, you add them in the same direction. We also, if we want to make stuff shorter, we can subtract vectors. But we need to just be careful if we say like, all right, so maybe I go 3 inches forward and then back 1 inch. Then my resulting is 2 inches. So we have to assign directions, right? Maybe to the right is positive and back is negative. And then you say, oh, this is -1 because it's to the left. But you have to decide those directions up front. Okay. So let's look at a real problem and try and figure out how fast something's going. So it says, a group of friends are going boating on a river. They check the news before leaving, and the news tells them that today the river is going 4 meters per second, right? So we've got let's see, here's some shore, and then we've got a beautiful river down here, and then here's the other shore. Okay, and we're going to boat across this thing. We're going that way today. So the river is going to be flowing this direction at 4 meters per second. The boat that they're on, what do boats look like? Right, here's their boat. This thing is going to travel in that direction at 15 meters per second. So if their boat points straight across the river, right, we're going perpendicular to the flow of the river, perpendicular to the flow, what will be their total velocity? So if you do this, I don't know how many of you have ever been boating before. If you haven't, maybe you should try and find some friends that have a boat. It's pretty fun. This boat is going to go, why did that ungroup? Group again. This boat is going to travel this way. Because the river's flowing, this is actually going to drift a little bit because the river is going to apply some kind of force to it and carry it along a diagonal. So what we can do to figure out the total velocity, or maybe the net velocity if you want to call it that, we want to figure out what is this velocity where they're going this way because of the drifting river and because of the motor on their boat. So we have a 4 meter per second component to our new velocity vector going this direction. So we'll put that as 4, and this is in the x direction. We'll call this Vx. Remember, this is all vectors. It's not just forces, even though the first two were force questions. Then we also have a 15 meter per second y component to our velocity. V in the y direction equals 15 meters per second. We want to know, what is our total velocity? How fast is the boat going? Like if I had a drone flying above it and the drone could only go 15 meters per second, it wouldn't be able to keep up with the boat because the boat's going 15 meters per second this way and the water's carrying us 4 meters per second that way. We have more than a total of 15 meters per second of velocity. So basically we're asking, what is V? Or maybe what is the speed, right? Because we don't really care what the direction of this is right now. We just care what's the number for this. What's the speed of the boat? All right. So what we need to do is Pythagorean's theorem. We're looking for the hypotenuse of this vector made out of a y and an x component. We know the components, we want the total. So Pythagorean theorem. So a squared plus b squared equals c squared. So we have 15 squared plus 4 squared equals c squared. 225 plus 16 equals c squared. 241 equals c squared. And then we take a square root on both sides and we plug it into our calculator very carefully, 241. And our velocity, the c squared, this is v final. Okay? V equals 15.52 meters per second. So we're going a tiny bit too fast for the drone, but all right. So that's one way we can look at vectors. Let's do one more problem just to make sure we kind of have the idea. So it says a group of friends are going boating in the river. They check the news before leaving, and it says the river is flowing at 4 meters per second today. So same setup, right? We still have our river. We're still boating that way across it. The river is still going 4 meters per second that way, and our boat can still propel itself at 15 meters per second. Now it says they angle their boat so it's going perfect, so that it goes to perfectly cancel out the flow of the river so that they drift straight across. So basically what they're trying to do here is they're going to turn their velocity so that the resulting velocity is perfectly aligned with the river. They're going to use some of their 15 meters per second to cancel out the 4 meters per second to get them going straight across rather than drifting downriver. So how are we going to figure this out? Well, we know that the river is flowing at 4 meters per second. So we have a 4 meter per second this way. Then we have a 15, and this is not going to be to scale. Disclaimer. We have a 15 meters per second velocity that we can point in any direction we want. These keep coming ungrouped. So we need to point this so that we're canceling out this 4 meters per second. So if we drag this over here, we're going to turn it a little more. That looks good to me. So we've turned it so that the components of this, we have that y component, and we have now a negative 4 meter per second component there. What we're looking for is if the river is 600, this should say meters across, how long will it take them to get to the other side? So we're trying to solve a couple of things here. We're trying to figure out the time it'll take to get across. We know a distance. we need a velocity. We need to know how fast are they crossing the river. Well, this 4 meters per second will cancel this 4 meters per second. We need to figure out this piece here, the amount of the velocity that they have going across the river. We don't know this. It's not 15. What's 15 is this diagonal piece here. This is 15. So now we're going to try and solve for this Vy. Then what we can do is we can take this velocity. We know the distance. Constant velocity, right? They're going this set velocity. We're not accelerating. So acceleration term goes away. 1/2 at squared. A0, this goes away. Plus v naught t plus x naught. We'll say this side of the river is 0. This goes away. So we're looking for our velocity. This velocity, our final velocity, right? And then we'll be able to find time. So we have aligned this so that the 4 meters per second cancel out. We know this diagonal is 15. We need to find this new y here. So let's use our Pythagorean theorem. Our hypotenuse, c squared, is 15. Squared, equals vy squared plus -4 squared. So the squared will get rid of the negative and everything will work out in the end. So vy squared plus 16 equals 225. Subtract the 16. Vy squared equals, quick maths, 209. Then we take a square root. Sorry, behind the scenes, we're taking a square root. And we get Vy, Vy equals 14.46, rounding, meters per second. So if we use some of our velocity to cancel out the flow of the river, we're still going to be able to cross at a rate of 14.46 meters per second. Now we're just going to plug our numbers in. X final is going to be 600, because that's how wide the river is, equals 14.46 meters per second times time for how long it's going to take to get across the river. We just divide by our component of velocity that's crossing the river, 14.46. And we get that our time is going to be about 41.5 seconds. So a little less than a minute to cross the river. So we're going to be doing more practice with this. Today, you're really just going to be working on breaking stuff down into components and then maybe solving some resulting adding and subtracting vector problems. So hopefully it's not too bad. Things will get a little more interesting when we start looking at forces and forces pulling in different directions and things moving horizontally and then falling or rising. It'll be fun. So until next time, please have a great day.